Hello everyone, today I'll talk about the solution to the problem My Calendar 2. This is a very similar problem to yesterday's daily. In yesterday's problem, we had to avoid creating any non-empty intersections, so any overlapping in bookings. Here we can allow bookings to overlap, but we cannot have more than 2 bookings overlapping at any given time. And of course the previous problem I've solved with a balanced binary search tree with the implementation from PyRival. But here I'm going to showcase another approach, a simpler approach, because we can afford to have an algorithm that works in quadratic time. So in essence, an algorithm that iterates over all the bookings that we already have whenever we have to add a new booking. It's possible to solve this problem faster, and I'll talk about it at the end of the video. A pretty natural idea when it comes to a problem like this, since we want to avoid triple bookings but allow double bookings, is to both keep in mind all the bookings that we have, so all the non-overlapping intervals, but in this case they can also overlap, and we can assume that there are no triple bookings at any point, so maybe this small interval here. And in order to make our calculations easier, we can also maintain another list of all the double bookings. And now when we want to add another interval, we first look at all the double bookings. If there is a non-empty intersection with any double booking, that would create a triple booking, we reject the new interval. Otherwise, that new interval does not create any triple booking, but might create some double booking, so we go through all the single intervals. And whenever we have a non-empty intersection, it is a new double booking. So this thing will always be non-intersecting, this list of double bookings. This list of intervals consists just of the intervals that we are given at the beginning. So for the implementation, they can both be lists. To see if 2 intervals overlap when we are given their starts and ends, probably the fastest way is to look at the maximum of the starts and minimum of the ends. The logic here is simple. That's because 2 intervals overlap if their overlapping interval is non-empty. And now, what do we know about this overlapping interval? Well, since it's the interval for an overlap, it cannot start before both the first and second interval starts. So it starts not earlier than the maximum of both starts. And also, it cannot end after one of our original intervals has ended. So it has to start so it has to end at most at the minimum of the 2 ends. And so it's easy to see that if this is a non-empty interval, then clearly this is an intersection of the 2 intervals. Otherwise, since those 2 conditions are very natural for the intersection, if this end that we generate is smaller than this start, that means that they do not overlap at all. And now, to check, of course, that overlap, we can just subtract start from the end and look at the sign of the result. So this function will calculate the overlap, and of course it returns none if there is no overlap. We are here using a decorator for static method, so that we don't have to write self as the first parameter. But we'll still call it self.startEnd startEnd. And the whole algorithm, we take the interval start-end, so we look at starts and ends in the double bookings. If there is an overlap between those 2 intervals, so if this is not none, we return false. Otherwise, we can add this interval, and we will add it, and that might create some double bookings, so we go through all the single bookings, we look at all the overlap, and if that overlap is none, then we don't have to do anything. Otherwise, it's a non-empty overlap, we add it to the list of double overlaps. Those lists are of course not really ordered. And at the end, we just append our new interval as a single interval to the first list. And at the end return true. Some things for you to think about. I said that those lists are not really ordered. You might find it enjoyable to think a bit about what the ordering will actually be of this double booking list. Another thing is, we do not connect intervals together. So for instance, we can have in our double booking list, and of course in single booking as well, we could have an interval that starts and ends at the same spot. Here, of course, there are very big intervals overlapping, so maybe if we were to connect those intervals together, then we might have a smaller number of intervals, but can we do it without sorting? But is it really necessary? So for instance, are you able to construct a test case that generates a very big number of these double overlaps? Because number of intervals here is just the number of calls to our book that happened before, right, to the book method. So it's bounded, but is it possible to make this thing much bigger than the number of calls to the book method? And if not, try to show it, try to argument for it. And of course, in order to solve this problem faster, this solution can be easily extended, assuming that you have a balanced binary search tree, to one that amortizes to n log n. We just have to do all the operations on a binary search tree. So since in Python that's not really very easy, unless you have, of course, sorted containers, but you typically don't have it. So if you want to try your own implementation of BST, then this is a nice situation, right? Because, again, to find overlap with this non-overlapping list, you can just do a simple search on the tree, simple lower bound. It's the same as the previous problem. And to generate all the doubles, you start at some interval here and end at some other interval here. But the question is, of course, how many steps that can take, how many double intervals will be generated, and does it amortize to something? Do we have to merge overlapping intervals? Since, of course, if you look at all the intervals in the first array that are overlapping with your interval, then you can merge all of those together. The new interval that you'll add and all the intervals that touched it can be merged together. So that's one n log n solution with amortized log n for the booking operation. And of course, another solution is to use some range add, range sum, range max data structure, such as a segment tree or a Fenwick tree. And probably the easiest solution that you can see is that when adding an interval, you just add one on the whole interval that it represents. And now there is an overlap if the sum with some other interval, if the sum before we add the new interval is greater than 0. And of course, we can also check the maximum to see on how many intervals that given spot lies. So for instance, if the maximum, we want to add an interval here, then our maximum will be 2, because at some point there are 2 overlapping intervals. So we know that we cannot at this point add this new interval because it overlaps. So we can use those data structures. Then the problem is that our starts and ends can be pretty big, and we have to solve this problem online. We cannot just read all the starts and ends at the beginning and then try to coordinate compress. So you would have to use an implementation that is dynamic, that only creates nodes that are necessary, and large portions of places where nothing happens on the line are represented in a compressed form. So those are exercises for the watcher, but in this case, as I mentioned, an n-squared solution is fine.